Good morning, everyone. Welcome back. Thank you for joining us. I'm Steve.
And I'm Scott.
And together we are Backyard Musings, the Science and Technology channel.
Definitely talking about a science issue today. This is pretty cool. More quantum computing.
Developments in quantum computing. A new chip scale device offers unprecedented control over laser frequencies, a key ingredient for large scale quantum computing. Researchers have achieved an important step forward in quantum computing by developing a device so small that it is almost 100 times thinner than a human hair. Thinner than a human hair. The advance was reported in the journal Nature Communications on December 8th, 2025. Would you like to know more?
The research centers on a new type of optical phase modulator designed to precisely control lasers. This capability is critical for future quantum computers, which will rely on thousands or even millions of qubits, the basic units of quantum information, to perform complex calculations.
A key part of the achievement is how the devices are made. Instead of relying on specialized hand built components, the researchers use scalable manufacturing methods similar to those behind the processors found in computers, phones, vehicles, and home appliances, virtually everything powered by electricity, even toasters.
The work was led by Jake Friedman, an incoming PhD student in the Department of Electrical, Computer, and Energy Engineering at the University of Colorado in Boulder, alongside Matt Etchenfield, a professor, and the Carl Gustafson Endowed Chair in Quantum Engineering. Okay, that must be pretty important.
It is.
They collaborated with researchers from Sandia National Laboratories, including co-senior author Nils Otterstrom, to create a device that combines an extremely small footprint with strong performance while remaining affordable to produce at large scale. Okay.
The chip operates by generating microwave frequency vibrations that oscillate billions of times per second, which are used to control laser light with exceptional accuracy. By harnessing these rapid vibrations, the device can precisely adjust the phase of a laser beam and generate new laser frequencies with high stability and efficiency. These capabilities are considered essential for advancing quantum computing, as well as emerging applications in quantum sensing and quantum networking.
Among the leading approaches to quantum computing are trapped ion and trapped neutral atom systems, which store information in individual atoms. To operate these qubits, researchers talk to each atom using precise laser beams, allowing them to give the instructions to do the computations. Is that still mine?
No, fine. It's
That's yours.
mine.
All right.
Each laser's frequency must be tuned with extreme accuracy, often to within billionths of a percent or even smaller. Quote,
Wow.
creating new copies of a laser with very exact differences in frequency is one of the most important tools for working with atom and ion based quantum computers, Friedman said. But to do that at scale, you need technology that can efficiently generate those new frequencies.
Today, those frequency shifts are made using bulky tabletop devices that consume significant amounts of microwave power. Current setups work well for small lab experiments and quantum computers with small numbers of qubits, but they cannot scale to the tens or hundreds of thousands of optical channels required for future quantum computers.
Quote, you're not going to build a quantum computer with 100,000 bulk electro-optic modulators sitting in a warehouse full of optical tables, Eichenfeld said. You need some much more scalable ways to manufacture them that don't have to be hand assembled and with long optical paths. While you're at it, if you can make them all fit on a few small microchips and produce 100 times less heat, you're much more likely to make it work. Oh my gosh.
Yeah, the device can generate new frequencies of light through efficient phase modulation that consumes roughly 80 times less microwave power than many commercial modulators. Using less power reduces heat and allows many more channels to be placed close together, even on a single chip.
Together, these features turn the chip into a powerful, scalable system for managing the complex dance that atoms must perform to make quantum computations. One of the most significant aspects of the project is that it was produced entirely in a fab or foundry, the same type of facility used to make advanced microelectronics. So a fab it's like a clean room. You got to wear head to toe garments with a face mask and everything.
Yeah, it's like a suit, white suit. Yeah.
Yep. Yep.
CMOS fabrication is the most scalable technology. This is a quote, by the way. Humans have ever invented. Etchenfield said. Every microelectronic chip in every cell phone or computer has billions of essentially identical transistors on it. So, by using CMOS or CMOS fabrication, in the future, we can produce thousands or even millions of identical versions of our photonic devices, which is exactly what quantum computing will need.
According to Otterstorm, I don't know if it's Strum or Storm, they've taken modulator devices which are previously expensive and power hungry and made them more efficient and less bulky. Quote, we're helping to push optics into its own transistor revolution, moving away from the optical equivalent of vacuum tubes and towards scalable integrated photonic technologies, Otterstorm said.
Why did you get a chuckle out of vacuum tubes?
Because that's like old. That's like in the 50s.
Oh, okay. The team is now developing fully integrated photonic circuits that combine frequency generation, filtering, and pulse carving on the same chip, bringing the goal of a complete operational chip closer to reality. Moving forward, they will collaborate with quantum computing companies to test versions of these chips inside state-of-the-art trapped atom and trapped neutral atom quantum computers.
Quote, this device is one of the final pieces of the puzzle, Friedman said. We're getting close to a truly scalable photonic platform capable of controlling very large numbers of qubits. All right, folks, thanks for joining us.
Okay, we'll see you this afternoon. Thanks.